Okay, so let's start. We will finish testing in this class. Just a few slides left. So how to evaluate tests. So you need to evaluate the results by comparing with the goals in the test plan, preparing metrics to determine the current quality of the software. So the reason to have metrics is to have a way to determine when to stop testing. As we saw before, even for very small toy programs, you cannot exhaustively test the software, which means that you can never be sure that your software has no bugs. It's not possible. Therefore, you must define the criteria to stop at a certain point. So you can consider testing completeness, that is percentage of test cases that have been run and percentage of code that has been tested. Of course, 100% coverage when it's not feasible. We strive for a smaller percentage of coverage within the deadline. Reliability is based on trends in testing error rate when compared to previous projects. So this is the failure rate plotted against the testing time. So testing time is perhaps measured in weeks or months. So based on previous projects, perhaps you have the expected failure rate plotted in the blue curve, and you compare it with the actual failure rate to interpolate where you are in the testing process. Say, for example, if you're somewhere in here and you look at the trend, and perhaps you can expect the failure rate to decrease along with similar rates, right? So you can interpolate, say, 5 months into the future or 1 month into the future, what's the failure rate going to be? And you can do some resource planning this way. So notice that the actual failure rate may be increasing a little bit near the end, which is normal, because by fixing old bugs, you may introduce new bugs. So you may see a small increase. So possible outcomes based on this is to make a decision at any given at a point in time to perform additional tests to find more defects, or to relax the test criteria. That is, reduce the percentage of coverage you try to achieve if they're set too high and to be unrealistic, or deliver acceptable parts of the system and continue revising and testing unacceptable parts. So perhaps the critical parts that the customer really wants are tested thoroughly, and their quality is determined to be high enough to deliver. Perhaps there's not enough time or resource to test the less important parts. You can leave them to be delivered in the future. So the decisions will obviously based on project-specific information and the failure rate. So testing often happens under pressure because most testing activity is done near the end of the project. So all tests are important, but you need to restrict testing in some way, limit its scope, and limit its time and resources required. So testing a system's capabilities, functionality is more important than testing its components. That is, what the system can do from the user's perspective. So it's important to identify things that will stop users from doing their jobs. so-called showstoppers. So even if you have a completely bug-free set of components, if the system is not doing its job, it's not performing its functionality, it's useless. So obviously the functionalities at a high level is more important. So, and also testing old capabilities is more important than testing new capabilities. Say you're doing a new product release, Office 2007, and you have an old version of 2005, so you're adding some new capabilities. Obviously, anything that had worked before should not be broken. It's important to keep that previous functions keep working. And that's what the users expect. So for the new features, perhaps if something doesn't work and the delivery deadline is near, you can remove those features, but you should not remove any of the new and any of the old capabilities. Testing typical situations is more important than testing boundary cases. So it's important that the system work under normal usage patterns. That is, perhaps 95% of the time, the system will be used with a certain workload and a certain range of inputs. So if you make the 95% situation work, the customer will likely be happy. But even if you crash or malfunction once in a while, for boundary cases, say if the customer types in some really strange values, then perhaps it's not as serious as breaking the common case. So always make sure that the typical case, the sunny day scenarios work. So summary of testing. First is good planning. Know what you're trying to test for, and have realistic goals set for testing, and base your research and time planning based on the goals. And use the right test in the right situation. Choose the appropriate white box, black box, and regression tests. White box tests are used for unit testing, component testing, and perhaps integration testing a little bit. And black box tests are used for integration testing and acceptance testing and system testing. Regression tests are used whenever you add something new to a piece of software, or do some upgrades or fix some bugs. You always run the old tests to make sure that nothing have worked before is broken. So test systematic and thorough. Have a testing strategy. That is when to run what. Unit integration, system acceptance, as we saw before. We have this testing from inside out, right? We had a slide on that. So you're developing the systems from requirements down to analysis, design, implementation, from outside in, and you're testing from inside out. When you write the smallest components, you do unit testing. And as you integrate the components together into subsystems, you do integration testing. And then you do the system testing when the system as a whole has been built, and finally acceptance testing. So that is a strategy that's systematic. And a clear criterion for knowing when to stop. So decide beforehand how much testing will be enough. Define your criteria, and use the past project failure rates as the guideline to help you make the decision. And whether you continue testing or stop now, deliver the critical parts, or stop altogether. So, okay, that's the end for testing. So we move on to quality assurance. So, software QA. So the goal is to understand the quality assurance process and understand the importance of standards and metrics in the QA process, and understand software configuration management, and understand software development process improvement. So software QA. So it is. I'd like to show you the. Yeah, it's in the end. So software QA consists of procedures, techniques, and tools applied by professionals to ensure that a product meets or exceeds pre-specified standards during its development cycle. So this is a sentence describing the general QA procedure. So software QA is a type of QA. Any company needs QA. A furniture company or any kind of manufacturing operation, they all need QA. So quality assurance defines organizational standards that lead to high quality software. So this, we're moving into the manager's job area now, instead of just a software engineer's job. So it's an organizational standard, not just purely a software standard. So it requires quality planning. QA, you have these defined standards, industry standard or your company's own standard, and then you select these standards and tailor them to a specific software project. So quality assurance, the definition of standards specifies what to do, and planning actually specifies how to do it for your particular project. And quality planning requires quality control, monitoring and control to ensure that standards are followed. So continuous quality improvement should be the overall goal. By that we mean continuous improvement over the lifetime of the company, over the years. So you should have higher quality in the next year than this year. And as the time goes by, your company becomes more and more mature and delivers higher and higher quality products. So we saw this statistics before. So this is saying when bugs or defects exist in the system, the earlier you detect it, the cheaper it is to fix. So suppose you have a baseline of 1 unit as the cost in terms of either time or money to fix a defect in the requirement stage, then it gradually increases to up to 80 to 130 when you detect the defect in field use. That's when you have to do product recalls and damages to the company reputation, etc. So, SQA activities pay off here because defects are cheap to fix. Instead of leaving them to the system test and field use when the cost will be very high. So you need to do QA throughout your development process. So now QA, as we see here, is really part of the management workflow. While all the others we discussed before, requirements down to testing, are part of the engineering workflow. So it happens from the very beginning to the very end, with little more focus in the construction phase. But it's really a pervasive action. So as you go down, remember each iteration goes from top to down, from requirements down to implementation testing. You always do QA at every iteration. So QA activities, standards development and application. So the standards help ensure repeatability of the development process. But in many organizations, you may not have standards. But many large companies do have rigorous standards. And also some particular industry have their own standards, like the defense industry. If you're developing software for a military airplane for the US Department of Defense, they have this standard called DO-178B that you have to follow in order to become their contractor. Metrics, development and application. So this is for measuring how well you're meeting your goals. So these are concrete metrics to help you monitor and control the process. Otherwise, it's a lot of guesswork. And applying software engineering methods and tools, these include the say different development processes like waterfall or spiral. These are different methods, and software tools, including configuration management tools, which we'll discuss later, and other tools for QA, like testing tools, test automation tools, etc. Formal technical reviews. Reviews are the meetings you hold with within the company, within the project, and people read other people's code, not just code, but also design and analysis documents, and provide a critical review at different points in time. So software configuration management, this is for controlling change. So that is, you may have many source files for your project, and everyone is working on different parts of the system. So you need to manage the different versions of the files to help control the changes. Otherwise, it could be out of control, and your software will never build correctly. So testing is an important part of QA. Helps to detect bugs, detect defects. But it's only a part. QA is a lot more than testing. So if you look for a job, sometimes you see the job title QA engineer. They're often referring to testers. But really the QA is a much more pervasive management activity, not just testing. So these two are the foundations of QA. So we'll go into more details. A technical standard is a norm or requirement that establishes uniform engineering or technical criteria, methods, processes, and practices. So that is a very very general statement. That is there are two types of standards important for software engineering. One is product standards, one is process standards. So the product standards are concerned with what outcome is produced and define the characteristics that all product artifacts should exhibit so as to have quality. So these are concerned with how good your final product is. So, and process standards are concerned with how the outcome is produced and define how the software process should be conducted to ensure quality software. So this is describing the process of developing the software. That is focusing on the keyword how, while the product standard is focusing on what outcome is produced. Obviously, product standards are the final goal. Process standards are just a means to achieve product standards. But process standards are necessary, perhaps not a sufficient condition for product standards. If you have a low quality process, everything is chaotic, and there's no standard procedures and processes, you're less likely to achieve high quality products. So, but higher process standards means that you try very hard. That is, your process is rigorous, and as a result, you're likely to get a high quality product. So why are standards important for software QA? Because they encapsulate the best practices or the most appropriate development practices, which are often acquired after much trial and error based on many people's experiences in your own company or in some other companies. So by codifying these practices into standards, and you follow the standards, you can avoid many of the pitfalls people have experienced before. Help to avoid previous mistakes. They provide a framework around which to implement quality control to ensure the best practices are properly followed. So the standards specify, dictate the way you do quality control so that you know what to measure and what to monitor to ensure that your development process are following the practices. It helps in ensuring the continuity of project work, reduce learning effort when starting new work. That is, perhaps a new developer comes on board, and it's easy to bring him up to speed if you have a institutionalized standards. And also, when you start a new project, you can quickly get up the learning curve based on a specified standard, instead of inventing new things every time. So standards handbook is needed. You have the handbook for different standards. Obviously, you need to customize it for your own project. So each project needs to decide which standards should be ignored, used as is, modified, or created. So this handbook is not a law. That is, you should customize it for your own project. So metrics. So just a brief. The foundations of the tool are, one is standards, one is metrics. So now we discuss metrics. So a metric is any type of measurement that relates to a software product, process, or related artifact. So we learned one metric before, cyclomatic complexity, for measuring the control complexity of the software. That is, how many different paths you can take through the software. So there are many other types of measurements, metrics. So why are metrics important? Because they can be used to control that is manage and plan to manage the development process. So metrics include effort expended, that is how much money has been spent on this particular subsystem, how many developers are devoted to any part of the project, elapsed time and budget spent. So these are the stuff you want to control, and metrics are used to control these time and budget efforts. So metrics can be used to predict associated product quality. So cyclomatic complexity can predict the ease of maintenance. If you have a piece of a software component with very high cyclomatic complexity, it implies that it's hard to maintain, because if you change anything, it's likely to cause a lot of effects throughout the software. So metrics are the only objective way to measure quality software, quality attributes of the software. Otherwise, it's all opinion and guesswork. So we have some metrics examples next. So we saw this picture before, 4 Ps. So people, software engineers. So by software engineers, we imply we have developers and testers participate in the project guided by a process like waterfall, like other process, unified or other processes. So the process is a template that you need to take and customize it for your own project, and finally you deliver a product. So how to achieve software quality? So there are you need to focus on each of the 4 Ps. So first, product quality. So you can measure product quality by testing, and by measuring the defect rate, and by measurement of different metrics to infer the product quality. So people, you need to education and training to give them the necessary skills, and project, you need management and monitoring. This is the topic of the next chapter on project management. So finally, you have measurement and feedback to the process. By this, we mean as your company has been developing many, has been working on different projects over the years, you should have a continuous feedback of what worked before and what didn't work, and into your process, so you can better customize your process in any future projects. So obviously, the ultimate goal is to have the product quality, and all the others are just means to achieve product quality. So it's very unlikely that you can achieve product quality if you have poorly managed projects, or poorly skilled developers, or poor process, or missing altogether an ad hoc process. Then your product is likely to be of low quality. So that's why you need all 4 Ps in this picture. So quality attributes. We should have a set of quality attributes that a software product must meet the design goals to achieve. So we discussed many of the design goals before, like reliability, security, portability, usability, learnability, efficiency. So you need to pick and choose a subset of the goals for your own for a particular product. And we need to be able to measure the quality of a software product. So to determine how well the product conforms to the design goals. That is, most of these design goals are really qualitative goals, like the software system is maintainable or portable. So how maintainable, how portable, right? How do you have an objective measure of that? So that's the job of the metrics. So we'll see some examples. And metrics also help you to track the values of the quality attributes to assess over time how well we are doing in achieving the design goals. So we should use information about the quality of any developed software to improve the quality of future software products. That is the feedback arrow into the process box in the previous picture. So you learn about your mistakes and try to improve your future processes. This is so-called continuous quality improvement. So design goal is an external attribute that we want a system to have, such as all these. So-called ilities, because most of these words end with ility. So it's an external attribute. That is, these are the attributes from the user's point of view who doesn't care about your internal implementation. Now, however, we can only assess whether a system has one of these attributes after it's completed. That is, when it's done and when you actually use the system, then you can assess perhaps usability and reliability and other attributes. So external attribute cannot be measured directly from the software. That is, you have a piece of software with perhaps 200 files and a million lines of code. But looking at the software, you don't know. You can't really measure all these ilities, all these quality attributes. So we would like to assess whether we are achieving a design goal during the system development. That is, keyword is before the product is finished, before you can even use it. So how do you do that? So try to use internal attributes to predict external attributes like design goals. Internal attributes are the things that you can measure from the software. That is, you can take the source code, feed it into a tool, and the tool can actually measure, say, the lines of code, or cyclomatic complexity, or number of components, number of modules, the degree of coupling, etc. So these are the internal attributes. So example of relationships between external and internal attributes. So internal attributes include number of parameters for function calls, cyclomatic complexity, lines of code, number of error messages, length of user manual. So maintainability is linked to all four of these. So the more lines of code, the harder it is to maintain, obviously. And also number of parameters affects the maintainability. And usability relates to a number of error messages and length of user manual. So not just number of error messages, you should try to make your error messages informative and relevant. So how many times do you see an obscure compiler message, error message that you don't know, doesn't give you any hint as to where your code is wrong? So that's not very helpful for usability of the compiler. So it's hard to formulate and validate relationships between internal attributes and design goals. So let's see, a simplistic approach is to just say, okay, maintainability depends on these 4 parameters. All these 4 can be measured automatically with a tool. So how about I just take a weighted sum of these 4 attributes, say 3 times cyclomatic complexity plus 2 times length of code plus 1 times error of number of error messages. But that's very arbitrary. The relationship is perhaps not even linear, and you cannot do a simple-minded weighted sum of all the internal attributes. So therefore, you need to collect, calibrate, and interpret quantitative software information. That is, you collect these internal attribute information, and you correlate these internal attributes to the external attributes design goals, and calibrate it to the particular company, perhaps based on previous statistics. You can predict the current project quality based on internal attributes. So this is could be a very complicated process to determine the appropriate relationship of the internal and external attributes. So, so automation of data collection can help you reduce time and cost. So, in the detailed notes, there are more examples on the these internal attributes. For example, one is to measure the input-output degree of each component. So each component takes a bunch of inputs and produces a bunch of outputs, right? If you have a component with 1 input and 1 output, obviously it's more maintainable than a component with 200 inputs and 100 outputs. So you can take these measures and do some analysis to predict your software's maintainability. So review. Now we move on to another box in the software QA diagram, technical reviews. So reviews are the primary method for achieving project quality. So the previous two, we discussed a lot about product quality, including all the metrics. But for achieving project quality, reviews are the primary method. So reviews can happen all through the development process. After requirements capture, you do requirements walkthroughs. By walkthrough, we mean review. So a bunch of people gather in a room, and everyone walks through the requirements documents line by line and provide any critiques on the requirements. Similarly, you do analysis walkthroughs after analysis, design walkthroughs after design, code walkthroughs after implementation. This is when each developer gets up to the whiteboard and presents the code has written line by line, and everyone discusses the code. And finally, test plan review for at the end of the testing. So reviews can lead to early discovery of defects because you're doing it at the very beginning through the very end. So requirements analysis and design introduce 50 to 60% of all defects, and formal technical reviews can uncover 75% of these. So these are empirical figures collected from in-field statistics by software engineering researchers. So another item, software configuration management, is an activity executed throughout the system lifecycle to control the changes to the product and lifecycle artifacts. So the product is the final thing you deliver. The lifecycle artifacts include requirements documents, analysis documents, and design documents, and other artifacts. So to what do we want to control changes? So configuration management is all about change control, because you have many people in the team, everyone's working on something, so there needs to be some central authority to control who can make changes to what. So obviously we control programs and source code. So that's the what SCM is mainly used for. But also you also control documents and manuals, data, procedures, specifications, and plans, including test plans. So so each one is called a configuration item. So we need to control each of these items. Configuration item is an artifact to which we want to control changes. So we need to identify these items and support, control, audit, and report. So auditing is someone reviewing the procedures, and reporting is the communication mechanism within the team on the different changes. Say, if I submit a change request, is it approved or denied, etc. So each configuration item must be identified and described with a bunch of so-called metadata. Metadata is the data about an item, but not the item itself. Say they include the name, the configuration item type. Is it a source file, or is it a document? Is it a test plan? Project identifier. So which project is this item for? Change in the version control information. That is the history of updates to this particular source code. When and who checked in a recent version. Resources the configuration item provides or requires. Say, if you have a .cpp file, which .h file does it include? Say, if you have a executable file, which library file it needs to run. So pointer to the actual configuration item. So this could be the actual path to the source code location in your directory system. So all these are metadata, and that particular item itself is described by and identified by this metadata. So the configuration items also must be organized. That is to define the relationships that exist between configuration items. say an object diagram is part of a domain model. So I think this is really should be class diagrams. So that's for the usage of the term. So a domain model is a collection of many class diagrams. So perhaps one diagram should specify which domain model it belongs to. And perhaps the domain model is related to some use case model. That is, the use case uses the classes in the domain model. So that's related to. So this is what we mean by organizing the configuration items. So this information is used to define and construct a software library So that software library is a database that stores and manages and tracks all the configuration items. So here's the picture of a library providing facilities to store, label, and identify versions and track the status of the configuration items. So it looks like this shape is usually used to represent a database. This cylinder shape, and it's divided into 3 parts. One is the developer's workspace, used for everyday development. That is, the developer is free to update anything within its workspace. And you have a master directory used by, shared by all the developers, where you store and track promotions. So promotions, a promotion is a version that's reached relative stability so that it can be made public to the other developers. Perhaps the single developer has written a piece of code. You shouldn't make it immediately available to the others. You should test it and make sure that it's relatively bug-free before you make it available and promote it. So you have this check-in, check-out procedure for configuration items. That is, when you determine a particular item is of a high quality, then you check it in. And you need to modify it to check it out. And you work on it, you debug it, fix it, test it, and then you check it in to make it available to the other developers. And finally, the software repository is the database that stores and tracks releases. The releases are for the users. So it's a version that's made available to the users because it has met the quality control goals set by the quality control team. This after SQA. So especially for open source projects, it's very common to have frequent releases. So a baseline is a time or phase in the software development, usually at a milestone after which all changes must be formalized. That is to be controlled. Before the baseline is established, you can pretty much, the control is less formal. That is, anyone can check in anything. But after the baseline is established, usually you have a central authority, like the project manager, who's responsible for controlling any changes and make sure that anything other developers check in have high quality. So to become a baseline, the configuration item must pass a set of formal review procedures. If it's a document, it must pass the document review. If it's a code, it must pass the code review. And then, if everyone agrees, it can become a baseline and become part of the project software library. After this, a checkout procedure is applied to the item. That is, access to and change of the configuration item is controlled. So any modified configuration item must again go through a formal review process before it can replace the original item. So requires the version control mechanism. So this is for if you're using some configuration management tools like Microsoft Azure Safe, or on Unix you have some other tools. Usually you can check in, check out rather freely, but for this case, for after you establish a baseline, you don't allow developers to freely check in any code. Instead, everything must go through a review meeting before it can be checked in. So, change control. I think there's a hidden slide on. No, it's not in here. So anyway, change control, uncontrolled changes rapidly leads to chaos. That is, developers these are the developers or users. They may like to change parts of the system, but if you don't control the process, one change can have repercussions on the rest of the system. So you can rapidly lead to chaos. Therefore, change control defines a formal process for making changes to a project. So a change request is submitted by users or developers. So users can submit changes to the requirement. Developers can submit changes to analysis or design or implementation. So a change control authority could be the project manager, evaluates, decides, and issues an engineering change order. If approved, a change order is a document that says this change has been approved by the authority. Please do the change. And then the configuration item is checked out, changed, checked in after SQA, after review meeting, and version controlled. It's stamped with a version. So, and then the configuration item is made available for use. That is promotion. Promotion is when you promote it to become available to all the other developers. Release is when you release it to the users. So this whole thing is called a change control. This whole 4 steps. So auditing and reporting. So auditing ensures that changes have been properly implemented. That is, ensures the steps and procedures are followed when making a change. So verify the steps are followed. It's done by a QA group if SCM, software configuration management, is a formal activity in the organization. So the QA group must kind of watch over the developers to make sure that the formal change procedure, like the review meetings, the check-in, check-out, the promotions, are done properly. So obviously, for smaller companies, you don't have a dedicated QA group, and perhaps this is done by the project manager. And status reporting keeps all parties informed and up to date on the status of a change. So it's a communication mechanism among project members to help keep them coordinated. For example, it allows management to keep track of the progress of a change. How long is the change order taking to finish, and allows users to find out the status of a change request. So I submitted a request 2 weeks ago. Did it go through, or was it denied? So this is done by status reporting, perhaps automated by a software system, so that anything that any action taken generates an email. Status reporting allows management users to determine who made what changes, when, and why. So we have discussed product quality and project quality. So now we move on to process quality, and finally to people quality, the 4 Ps. So process quality. So does process quality imply product quality? If you have a high quality process, is it a guarantee that your product will be of high quality? It's often true for manufacturing. Once you have a high quality manufacturing process, the product quality will be good. Manufacturing is kind of a mechanized process with low-skilled workers. So the high-quality process, as long as the process is in place, no matter what workers you hire, they just do simple repetitive work. So they don't affect the product quality that much. But for software development, it's different, because it's a highly skilled work. And software engineers' skills and other factors affect the product quality a lot. So software development has some unique factors that affect the product quality independent of the process used. So it's designed, not manufactured. So the design implies a creative process, while manufacturing implies a repetitive process. Software development is creative, not mechanical. Individual skills and experience can have a significant influence. So sometimes people and technology are more important than the formal process in terms of ensuring the product quality. So for example, for small projects, the quality of the people involved may be more important than the processes used. So if you have some genius programmers, it can really help a small project. And for small teams, good development technology like good debugging tools and good IDEs are very important, as it affects productivity a lot. So that's people and technology. So people quality expertise and tools may have more impact on product quality than the processes used. Also, external factors like novelty of the application, competitive advantage of the company may also impact quality. So regardless of the processes used, if you have a highly novel product that has never been done by anyone before, then it's harder to achieve high quality. Obviously, manufacturer doesn't have this problem because everything is well defined for manufacturing. So insufficient resources will always adversely affect product quality regardless of the process used. So resources include developer resources and time and money, of course. So a detailed software development process is usually not transferable since it's highly organization specific. So as we discussed before, a process is just a template. You take it and customize it for your particular organization and for your particular project. Therefore, something that worked in your organization may not be readily transferable to some other companies, unlike manufacturing, where it's easily transferable. Therefore, the question here, the answer is that process quality does not imply product quality for software projects. So ISO 9001 and 9000-3 are the industry standards for process quality. So ISO 9000 was originally defined for any company, not just a software company. If you drive around in Guangdong, you often see many manufacturing factories with the large signs that says ISO 9000 certified. But ISO 9000-3 is defined for helping the client assess the process management capabilities of a software organization. That is, a client who is trying to hire a software organization to develop a piece of software. If the software organization has passed this ISO certification, then the client has more confidence in the software organization's management capabilities. So ISO 9000 in general specifies actions to be taken when any system, not necessarily a software system, has quality goals and constraints. So 9001 clause 4.2, this is a clause within a document, requires the organization to have a documented quality system, including a quality manual, plans, procedures, and instructions. The quality manual defines and documents the organization's quality process. That is a step-by-step instruction on how to ensure quality. And 9000-3 explains how the quality system should be integrated throughout the system development process. So 9001 and 9000 are general standards for any organization, and 9000-3 explains how this can be integrated in the software process. Specifies generic procedures that should be in place to have a quality process for software development. So we won't go into details on the ISO standards. There are more contents in the slides, but I won't discuss them. Finally, we come to the SEI CMM, Capability Maturity Model. So you may often hear this for some software company says we have passed the CMM -3 or -4 certification, etc. So CMM is a standard from SEI. SEI is Software Engineering Institute from Carnegie Mellon University in the U.S. So they define this standard to help a software organization assess and improve their development process. So they have essentially 5 levels. So initial process, ad hoc, is when the company has no formal procedures, no cost estimates, no project plans, no management mechanism to ensure procedures are followed. So this is essentially the baseline that any company can satisfy. So, and level 2 is repeatable process. So this is when you have basic project controls and intuitive methods. So this is when you have management control to track cost, schedule, and functionality, and some discipline among the team members, and intuitive process methods. That is, you don't have rigorous quantitative metrics. You only have kind of a sense, an intuition on how the development is going in terms of the quality of the product or process. So level 3 is a qualitative process. That is, the development process is defined and institutionalized, where the process for both management and engineering activities are documented, standardized, and integrated into a process, and all the projects within the company use the process. So that's so-called institutionalized. That is, it's defined into a rule for the company. You must use this process, and the process is more visible. So level 4 is managed process, as quantitative process, where you have concrete metrics for measuring the progress, and both the process quality and the product quality. You measure the all the metrics are recorded in a process database. That is, all the information you collect, like all the source code complexity measures or process metrics, they are collected, and a history of the company's all the projects are kept in a database. And finally, optimizing process is when you have feedback, improvement feedback. Remember, in the 4P diagram, we had an arrow pointing into the process box, indicating a feedback to improve the process. That is, you have rigorous defect cause analysis and prevention. You do a post-mortem analysis of all the projects and learn any lessons and to improve your future project in the future. So at level 5, CMM is extremely hard to achieve. So a level only extremely competitive software companies achieve level 5. I think in China there are only a few foreign companies like Motorola Software Center has achieved CMM 5. but in India, I think there are a lot more CMM5 organizations. Level 4 are like the US Space Shuttle program. The NASA software team has achieved level 4 or 3. And if you achieve level 2, then you would, it will be very easy to achieve the ISO 9000 certification. So it doesn't imply that you automatically get the ISO 9000. It just says level 2 is roughly on the level of the ISO 9000 certification. So this just shows you how difficult it is to achieve high levels of CMM. So what happens is that you invite the people from SEI to your organization, and they examine your documents from your past projects, and they ask questions, and then decide if you can be certified and to what level. Obviously, all these certifications should be taken with a grain of salt, because sometimes people can achieve certification, but it doesn't imply that they're really good software companies. You can sometimes you can fake the process, so to say. So finally, we come to the people quality, where we have people capability maturity model, PCMM. So this is intended for people development, what CMM does for software development process. So intended to assess and improve knowledge and skill of people. So you also have 5 levels. Level 1 is initial, where the organization provides no technical or management training. Staff talent is not a critical resource. That is, it's not valued in the organization. Knowledge and skills stagnate. People don't learn any new things. And no organizational loyalty. That is, people jump ships frequently. And repeatable, level 2 is repeatable. That is, focusing on developing basic work practices. Staff recruiting, growth, and development are important. You have training to fill skill gaps, and you have performance evaluations for the developers. And your compensation, your pay, depends on your performance. Level 3 is when you have you tailor the work practices to organizational business, and a strategic plan to locate and develop required talent, recruiting plan, and skills-based compensation. Staff are rewarded as they acquire core competencies and skills. So employees are encouraged to attend the training programs, because if you complete the training successfully, you get a small raise. Managed is when you focus on increasing the core competence in critical skills, and mentoring, team building. Mentoring is when the old developers help mentor and guide the new ones to come on board. Quantitative competence goals, evaluation of effective work practices, and finally optimizing is when you have feedback, again, for improving team and individual skills as the company develops develops more and more projects during the years, and use of best practices by collecting information from past experience. So PCMM is relatively obscure, so people don't really take this PCMM level as seriously as CMM level. But it's good to have it. Just the clients, when they look for a contractor, a software development organization to develop their software, they usually focus on the CMM levels. Obviously, perhaps PCMM is more important if you're looking for a job and looking at a company. So retrospective, an organization should have a quality manual which documents its QA procedures. So the quality manual could be based on standards like ISO 9000 or other standards, or it could be an in-house manual for this particular company. So each project should have a quality plan which sets out the design goals that are most important for the project and how they will be assessed. So there are too many design goals to satisfy all at once. You cannot hope to achieve very high reliability while also achieving a fast time to market. For example, you gotta choose which one is more important to you and how they will be assessed, right? So oftentimes the design goals can only be assessed after the product is finished. That's not good enough. You must be able to assess the design goals during development before the product is able to run. So to do that, you need to measure the internal attributes, like the lines of code, cyclomatic complexity, number of error messages, and infer the external quality attributes based on the internal attributes. Organizations should have well-defined standards for its software development process and the accompanying artifacts. So you should customize. Say you take the unified process as a template and you customize it for your own organization as your own standards, and you define a set of artifacts that you must produce during the process. Mechanisms should be established that monitor compliance with all quality requirements of the organization. So monitoring is usually done by the QA team. If the company is too small to have a QA team, then the project manager can do the monitoring. Reviews are the primary means of carrying out quality assurance. Reviews are also called walkthroughs, where people sit around and examine a requirements document or a piece of source code and provide critique, provide their opinions on this artifact. Where practical metrics should be used to highlight anomalous parts of the software that may have quality problems. So if your software modules have an average cyclomatic complexity of 10, and you have this one module with cyclomatic complexity 50, then it's a signal to you perhaps it's an anomalous part and you need to fix it by reducing its cyclomatic complexity to make it more maintainable. So quality software does not just happen. Software quality assurance needs to be built into the software development process. So as shown in the unified process diagram, it's a continuous process from inception down to the very end. So developing quality software requires management support and involvement. So because the QA and later next chapter on project management, they must take part in the quality control process. Standards that everyone follows gathering and use of software metrics they're used for predicting equality attributes and also for resource planning. Commitment to following the standards even when things get rough. So when things get rough, deadlines are near, people tend to go into a panic mode and start hacking without concern for any standards. So you should have a commitment to do that. Testing is an important part of quality assurance, but not all there is to obtaining a quality software product. So as the diagram shows, testing is just one box. We have standards, metrics, reviews, and all the others as part of the QA process. So we are finished with the QA chapter. I think we're a little ahead of the schedule, so I think I'll devote one class to do an overall review of the key concepts throughout the course. So, and also, I didn't receive any objections on the demo schedule, so we'll do the demo on the 10th of December. Okay. Okay. See you next time.